All right, so today's notes, we're going to cover section 2.2, which is solving inequalities using addition and subtraction. So we have a general idea of what it means to solve something. That just means get the variable alone. So what we have today is we're going to have problems that look like this: x minus 5, m minus 3, or even down here like s plus 18. The idea is we're going to try to undo addition and subtraction to get the variable alone. Recall that we undo using inverse operations. So we have these fancy addition properties and subtraction properties, and I'll leave them on the screen so you could pause it and write them down. But all it's saying, and you read the definitions, that if we start with an inequality, like let's say this one, and if we wanted to get x alone, if I add 5 to both sides of an inequality, then it doesn't change the answers from the original inequality. And what it means is we actually produce something called equivalent inequalities. So equivalent inequalities, this inequality, x minus 5 is less than negative 3, is equivalent to this one, x is less than 2, meaning they have the same answers. So we can use addition to undo subtraction in an inequality. Since this is so many numbers, all the numbers that are less than 2, we always make a graph. So we'll plot 2 on the number line. 2 will have an open circle, and 2 is being eaten by the inequality symbol, which means it's the biggest. So all of our numbers are going to be less than 2. And we just keep shading forever. Eventually we just put that arrow. So when we see number 2, if I wanted to get b alone, I don't want it to be subtracted by 2. So the addition property says we can add 2 to both sides without changing the solution set. So negative 9 plus 2 is negative 7, and that would be our final solutions. So this here and this here are equivalent inequalities because they have the same solution sets. So we go graph, so we put 0 on our number line, negative 7 is over here. Now at negative 7 we have a closed circle because of the equal to sign. And then our b value is being eaten, which means we are going to shade the numbers that are bigger than negative 7. So those are the numbers in this direction. And again, the arrow is just indicating it goes on forever. So we'll finish up the last two. If I wanted to get m alone, I would want to undo a minus 3. So I'd add 3 to both sides. So the plus 3 and the minus 3 would undo each other. And I have m is less than or equal to 8. So we put 8 on our number line. It's going to be a closed circle because it is included, right, or equal to. Now 8 is being eaten by the inequality symbol. In other words, the inequality symbol is opening towards the 8, which means 8 is the biggest. So we need to shade numbers that are smaller than 8. So all of these numbers are smaller. Now on this one, we want to get y alone. So here's y. I don't want to subtract 1/4 from it, so we'd add 1/4 to both sides. So 1/4 plus another fourth, that's 2/4. And of course, we'd simplify that to 1/2. So we'll put 0 on the number line. Since this is a fraction, we should probably put the integers that it's in between. So 1/2 is between 0 and 1. So we'll put an open circle there because we don't want to include the 1/2. There's no equal to. We can see that the 1/2, the symbol is opening towards that, which means 1/2 is the biggest, which means our stuff is going to be smaller. So we'd have to shade all the stuff that's smaller than 1/2, and that's stuff like 1/4, 0, -1, so on and so forth. Now the same thing works with subtraction, and that's what this subtraction property is saying. So if I was trying to solve this inequality, I want to get this variable by itself. I don't want a plus 18 with it. I want nothing with it, a 0. So to make the 18 turn into a 0, I'd have to subtract 18 from both sides. And as we said before, that subtraction property just says the same thing. If I subtract something from both sides, it doesn't change the answers. So here we just plot all the numbers that are bigger than 3 or equal to. So I want to put a closed circle at 3, and the symbol is opening towards the variable that I'm going to shade in. So those are the bigger things. So I want the numbers that are bigger than or equal to 3. Number 6, I want to get this x alone. I don't want a plus 2 with it. I want a plus 0. So to make it a plus 0, I'd have to subtract 2 from both sides. So that makes a 0. Negative 5.2, and if I have 2 more negatives, in total I have 7.2 negatives. And similar to how we did a fraction, this is in between two numbers, so we should place it appropriately in between those integers. Negative 7.2 is going to be a little bit closer to 7. So we'll place an open circle there because we do not want to include negative 7.2. And then negative 7.2 is being eaten by the inequality symbol, which means it's the biggest. So we want to shade things that are less than that number, and those would be the numbers that are more negative. So again, just summarizing on this page, we should be able to solve an inequality that contains addition or subtraction. And it seems really easy that all we did was add and subtract, and we reminded ourselves that if we do that to both sides, it doesn't actually change the inequality or the answers. And I want to just highlight that one more time. If I know that 3 is less than 5, if I add 1 to both sides, 4 is still less than 6. If I subtract from both sides, 1 is still less than 3. So addition and subtraction are really nice. They don't change the inequality symbols. But just prefacing, in some upcoming lessons, what we're going to notice is that that's not always true. If I multiply or divide, like let's say I multiply by negative 2, well, negative 8 is not less than negative 12. So it no longer becomes true. So sometimes when we multiply or divide, things become weird. So we're starting really easy and making sure we know that adding and subtracting don't actually change the inequality. So we're able to do that to get our answers. The last thing we have is just a few applications. So just using that information. So you have $25 to spend on groceries. We also have $15.75 worth of groceries already in the cart. Write and solve an inequality that represents how much money you can spend on groceries. So similar to a word problem, we want to come up with a fact. So if we're going grocery shopping, we think about money we have. We're going to compare that to money we owe, or what we're buying, right? And I think we would all agree that the money that I have in my wallet needs to be bigger than the money that I owe, or in a perfect scenario, they're exactly the same. So what is the money that I have? Let's go find that. Well, it says we have $25. So we're going to replace that with the number 25. Now, how would we figure out, so I'm just keeping that same inequality symbol, how do we figure out how much money we owe? Well, it already tells us that we have $15.75 already in the cart. So we'll add that to the money we owe. So we owe $15.75. But it also wants us to represent the inequality, how much more we could spend on groceries. So that's part of what we would owe. How much more would I buy? Well, they want us to call that M. So here's our inequality. I'm going to write it in black just to make it a little more clear. We're saying that 25 must be bigger than or equal to 1575 plus M. So that's step 1. We had to write the inequality. And to solve it, we're just going to summarize what we did before, right? I want to get M alone, and I'm able to get rid of the 1575 by subtracting it from both sides. We learned before that subtracting from both sides does not change the answers. So M is left, and if I take 1575 away from 25, that'll leave me with $9.25. So in other words, what that means is M is less than or equal to $9.25. So at most, we can spend $9.25 more. So we're going to go over the last example here. It says a number M is less than another number N, and the number N is less than or equal to a third number called P. So what they first want us to do is write two inequalities that represents these relationships. So I'm just going to split that up. So the first inequality, we know they compare two things at once, and they want us to compare the number M to the number N. And as it says right here, M is less than something. So if M is less than something, that means the other thing is bigger. So the next relationship that they want us to compare is between N and P. What it says here is that N is less than or equal to that number P. So we'll make it less than or equal to that number P. Now it wants us to describe the relationship. So let's make this a little more tangible. Let's put a number line here. So let's make up three numbers. So let's put M right here. That needs to be less than this other number called N. And to help you, maybe let's call that the number 1 and this the number 4. And let's make our third number. N is a little bit less than that, or it could be equal to. Let's just make it less. We'll call it P. Let's just put that at the number 10. So how would we describe the relationship between M and P? Well, it's very clear that if M is less than N and N is less than P, well then M must be less than P. Now letter C is kind of interesting. Could M be equal to P? So let's think about that for a second. If we still have n right here and we have p right here, if we put m right on top of it, would the things in part A still be true? And the answer here, I think, is actually no. So let's first talk about n being less than or equal to p. Well, that could be true. If n was right here as well, if they were all at the same exact point, that would be true. But if n was there, well, then this wouldn't be true. M would not be less than n because we said m was the same thing as p. So this one wouldn't make any sense, so m could not equal the number p.